Hey, what are you doing here?
Hey, I'm here to clean up the lab.
Oh, what's your name? I'm Jason.
I'm Kyle, nice to meet you.
Alright, are we the only two here?
I think so.
Do you want to start and grab a room?
Alright, yeah, I got you.
Boo! You suck!
A few moments later.
What the hell are you doing?
I'm cleaning.
With a broom?
Yeah, dude.
God.
Yeah, I'm bored, bro.
Same. Yep. You want to do an experiment?
With that?
Yeah.
Let's do it.
Bet.
Eventually.
Okay, Jason, what do we need for this experiment?
So we're gonna need the sucrose. I think you have it. The sulfuric acid's over here. The two beakers. You have that, right?
Yep, right here.
We also need the aluminum foil and the gloves.
Hey!
Nice. The graduated cylinder. Oh wait, I have it here. And some sodium bicarbonate.
Why do we need that?
Well, do you want to die?
Yeah!
Well, can you grab it so I don't die?
Alright, I think there's some right here.
Got it! Nice. Alright, want to start with this procedure?
Dope, let's get started. Let's go.
Next day.
Alright, man, I gotta go grab the sodium bicarbonate to neutralize this.
Alright, be quick, please. Here. Go faster. Alright, go.
Are we good? Alright, let's go. There you go, man. I think we can sell this.
Yeah, I think you're right, because we don't get paid for anything that we do in that classroom.
Yeah, let's go find some people to sell this to. Let's go.
3 days later.
Hello.
Hi.
So, I'm from Lincoln Park High School, and my name's Jason. I'm here with my business partner Kyle, and we're here to raise money for our school. And at school, we created this thing in our lab called the black carbon. Are you interested?
Oh no, but my boss might be.
Oh, really? Do you think that I could give you my contact info to your boss so that he can contact us if he wants to buy it?
Oh, yeah, definitely.
All right, let me grab it. All right, here you go. All right, thank you.
Thank you.
Have a nice day.
You too.
3 hours later.
Can you move it along? I'm all out of time cards.
Hi, Steve. Welcome to our lab. So I know that my partner Jason already gave you some information about the black carbon. So from here, this is our balanced reaction. So basically sucrose plus sulfuric acid yields 11 mole of carbon plus carbon dioxide gas plus 12 mole of water vapor plus sulfur oxide. So from there, we're able to determine the theoretical yield for the amount of carbon produced. So with 70 grams of sucrose in excess of sulfuric acid, we multiply that by 1 mole of sucrose over 342.2 grams of sucrose, multiplied by 11 moles of carbon over 1 mole of sucrose, times 132.12 grams of carbon over 1 mole of carbon, which gave us approximately 297.22 grams of carbon produced. So my partner will give you an intro into the redox.
Hi Steve, nice to see you again. So moving on to the redox reaction. If you don't already know, redox is when it's a process in which a molecule or a substance is reduced while the other is oxidized. From this reaction, we can see that carbon stays constant throughout the whole reaction. Hydrogen and sulfur are oxidized while oxygen is reduced. Any further questions, Steve?
No, that's great. But I have to go.
Oh, really? That sucks. I guess I'll see you tomorrow then. Bye-bye.
Alright, see ya.
Many months later.
Hi, Steve. Oh, you look a little bit different today.
Yeah, I got a haircut.
Oh, alright. Well, let's get into the molecular structure of sucrose. In sucrose, there's hydrogen bonding between oxygen and hydrogen, London dispersion forces, and as we know, London dispersion forces, or LDFs, are the weakest intermolecular forces, and it's present in carbon and hydrogen, and there's dipole-dipole forces between carbon and oxygen. Because of the relatively low attraction for the compound's atoms and the electrons, they have covalent polar bonding.
Okay.
Yes, any questions?
Continue.
Okay. And because of the greater difference in electronegativity between hydrogen and oxygen and carbon and oxygen, it's polar.
Okay, so are there non-polar bonds in
Yes.
sucrose?
In sucrose, because of the low difference in electronegativity between hydrogen and carbon, it makes them nonpolar. And overall, sucrose is a superpolar molecule.
Okay. Okay, I need somebody else explaining this.
Here.
Yeah. Hey, what's up, Steve?
Alright.
How you doing?
Good, how are you? Alright, so explain to me sulfuric acid.
Dude, I got you. Sulfuric acid. Alright, intermolecular forces, dipole-dipole. Between the bond of sulfur and oxygen, okay? London dispersion forces also occur throughout the whole molecule, but it's the weakest force. Hydrogen bonding, it exists between the bond between oxygen and the hydrogens, alright?
Okay.
Well, how do I know the polar, if it's either polar or nonpolar? Well, between sulfur and oxygen, and sulfur and the double bond between oxygen, they're polar because there's a greater electronegativity between the two, right?
Yes.
So therefore, we can determine that it's covalent polar bonding due to the relatively low attraction of the compound's atoms and its electrons.
Indeed.
Good, right? So that's why we know that this molecule is super polar. And then it's a strong acid because ions associate in water.
Oh wow.
You understand?
Okay, I want more. Somebody tell me, explain to me Gibbs free energy.
Dude, I got you. Ready? So from here, the change in heat, right? We know that it's negative, okay? The entropy, we know that's positive.
Yes.
The spontaneity is always spontaneous, right?
Indeed.
So from what my partner told you with the redox earlier, we know that sulfur and hydrogen are oxidized, right? In sucrose?
Yes.
So therefore, that heat release is sufficient to initiate the spontaneous dehydration reaction. Boom.
Thank you, but this is a load of crap. It is I, Sean D. McGuire.
Oh crap!